In this video, we'll be talking about r squared, or the coefficient of determination. Now, the reason for this video is that there's a lot of sometimes ambiguity over what r squared means, and the reason for that is sometimes in certain situations, such as when we have a linear regression, a linear model, we can make certain assumptions that we can't make when we have a quadratic model or something else. So because of that, people have difficulties interpreting r squared in certain situations. So this video is going to try to be very general, and for just any regression, for any prediction function, we're going to try to explain what does r squared mean, what does it represent, and we'll give a mathematical definition to go along with this. So we can start looking at it if we just have a scatter plot. Let's say all these orange points, we just have some x and y values, just some scatter plot. And let's say we fit, whatever reason, this kind of parabola looking thing, this green prediction function to it. Now naturally the question is, how well does this green prediction function fit these orange points? Is it a good fit? Is it a bad fit? That's why we need some kind of measure, which ends up being called r squared. So to explain r squared, we first have to kind of talk about variations. So let's make this concrete for a second. Let's pretend that the y variable, the thing we're trying to explain, is how much people spend on food. Now, there's a reason that not everyone falls on this purple line, which is the mean of the food expenditure. If everyone fell on this purple line, that would mean everyone spends the same amount of food, and there's no variation, there's no reason for anyone to spend a different amounts on food. But we know in the real world there are reasons, and we can just list two right off the bat. For example, family size. If you have 2 people in your house, then that household is going to spend a lot less on food than someone with 5 people in the house. Also, maybe it's linked to how much you make. Maybe if you make a lot of money, you spend a lot more on food than someone who doesn't make as much money. So we know that there are variable factors in the world that affect this is household expenditure, let's say, how much a household is going to spend on food. So there is a total amount of variation at least within our sample of each point from the mean of the points, and that's what we're going to call SST, or sum of squares total. And naturally we're going to define it like this. So let's just look at the inside part first, just this part without the squared. So if we have some point here, let's say this point is called x sub I comma y sub I. If we take y sub I minus y bar, that's the total variation of this household's food expenditure from the mean food expenditure of all these households. So that's going to measure how far off they are from the mean. Now we're going to need to square it, because for these points down here, if we just took that measure, it's going to be negative. So we just want the absolute distance. We could either do absolute values here, we'll just square it, just so we get a positive number, okay? And now we have the sum over I. So we're doing the sum for every single one of these orange points, because we want to know in the sample what is the total amount of expenditure. What is the total amount of variation in this food expenditure that we have? Okay. And then we can break this up into certain parts, because we have a prediction function. We have some function that's helping explain some of this variation, this total variation within our sample. So we have SSR and SSE. Now you need to be really careful about how you define SSR and SSE, because sometimes E stands for error, sometimes it stands for explained. In this case, it's going to stand for explained. I want to be very explicit. It stands for explained here, because sometimes you get swapped around. So maybe I should use better notation, but at least to be clear, I'll be writing out the word explained. Explain, okay? So this is explained. And this SSR, this R is going to stand for residual. So residual. I'll just write resid. Okay, so be very careful about, if you're reading a book or something, reading a paper, how they define their SSR, SSE. Sometimes people make it more clear by making more clear notations, which I probably should have done, but at least we know now. Residual and explained. Now let me explain what each of these mean. Let's go to sum of squares explained first, SSE. Now our model, our green model, you can see that it's explaining some of the variation. So let's again look at this point, this guy right here. Where the green point for him would be, the prediction function. It predicts his household expenditure will be right there. So we have that yi hat, so the prediction function, which is this value right here, minus y bar is going to be what? That's going to be this distance right here. So this model is helping explain this much of the variation from the mean for this household's food expenditure. So we still see that this much variation is unexplained by the model. It is not accounted for by the model. And because of that, we say it's the residual. It's part of the residual, so SSR. And we see that that is yi minus yi hat. So prediction minus actual, which we see that's exactly what this is. Because this is the prediction right here, and this is the actual. So the distance between them, between these two things, will be going into SSR, residual. So we see right off the bat that if we have the total variation, so let's say total, let's just do a very simple formula here. Total variation, I'll do this in marker. Total variation is equal to variation explained by the model plus the variation we have in the error. This is just a simple formula. It's not really part of the R squared. It's just trying to get us to understand where these total variation is coming from. So again, the total variation is the full length of this blue bar from this guy's food expenditure to the mean, the total variation from the mean. Now it's split into two parts. One is the variation that we explain through the model, which is again this section here, and the other part is the variation we cannot explain through the model, which is this error term right here, which is V sub E. Now, because we're doing squares and everything, we can't just say that SST is equal to SSR plus SSE, although we can say that if this was a linear model, but we're trying not to make any assumptions, so we can't say that right now. But we're ready to define what R squared is. So we're going to write down the formula, and we're going to explain why intuitively it makes sense to define it this way. We're going to say R squared is equal to 1 minus SSR over SST. Now let's put this in a box because this is going to be our definition for the video. Let's just go into what this means. So without even looking at the 1 minus part, let's just look at this part right here. What is SSR over SST? Remember, SSR is a measure of how much variation we cannot explain. So remember, SSR is this part right here, and we're summing the square of this distance for every single orange point. Right, so just to make another example, let's say we take this orange point, then we have that the total variation is just this, but the model predicts it to be all the way down here. So we would have, actually this is very unique because we have SS total is right here, just a small distance. We have that the residual, which is the residual would be this whole distance right here, residual. And then we would have the explained variation would just be this bit right there. Okay, so we do that for every orange point, and that's how we get we do the sums. So really this is this should not be SS, SS, SS. It's just SS when we take the entire sum. So this is just TV, V sub M, V sub E, okay? So this is it's a fraction, right? So it's the amount of error we have, the amount we can't explain, over the total variation. So if we look at just this fraction, what it kind of says is, what is the unexplainable percentage within our population? So it's the total amount of unexplained variation divided by the total amount of variation. So it's the percentage of unexplained variation because it's a proportion. Now when we take 1 minus, because 1 is the total amount of variation, right? And if we subtract the total amount of unexplained variation, then naturally what we're going to get is the total amount, we're going to get the percentage of, let me write this in marker, percentage of explained variation. So I'll write varn. So this naturally, this 1 minus the percentage of unexplained variation will give us the percent of explained variation. So what R squared is, if somebody stops you on the street and asks you very generally, you don't know if the model is linear, quadratic, cubic, whatever, they ask you what is R squared. What you should say is that it's a measure of the explained variation in the y variable. So the total variation in the y variable is just the variation from the mean for each point. We sum them all up after we square them. R squared measures, given some model, so given some green curve, whether it be linear, quadratic, whatever, it is the amount, it's the amount of explained variation, it's the amount of variation that the model can explain in the y variable. Okay, so if we had a tighter fit, so if we had a much better model, this is very unrealistic, so what I'm going to draw here, it's not very realistic. So if we had some better model, let's say it hit more of the points, it just went like this, it somehow hit all these points right here, it's hitting all these points, it's hitting a lot of points. Now this is really bad. You're never going to be able to make a model like this, and it's bad because it's overfitted, which we might explain in a separate video. But for the time being, it's hitting more of the points, it's going closer to more of the points. Our R squared would be higher, and why would it be higher? Well, it would be higher because this SSR, let's remember, is the residual. It's the distance from each of the data points to the model itself. These distances would be a lot smaller because they're closer. For example, let's look at this guy right here. Under the green curve, then the contribution to SSR, so the error, would be this much. But under the brown model, this new one we just did, it's just going to be that little portion right there. Therefore, this shrinks. Therefore, this whole fraction shrinks. Therefore, 1 minus this smaller thing is a bigger thing. So that's just kind of what R squared is. I know it's been very high level, but we have to be because we can't make any assumptions. We might make a video in the future. If it's linear, we can make a lot of different assumptions. One of the biggest assumptions, if it's linear, is that SST is actually equal to SSR plus SSE. We can't say that right now, but we could say that if that's linear. But that's kind of what R squared is. It's called the goodness of fit sometimes. It's coefficient of determination. It's a measure of how much variation the model helps explain. So hopefully that kind of helps.